In this video, our focus is on data. We'll take a look at constructing a data-driven model as a means of supporting the scientific method. Specifically, we'll investigate an objective method of making inference based on experimental results. To make our discussion more concrete, I'll ask you to imagine you're working for a pharmaceutical company. Suppose that company has developed a new drug. Suppose also that concerns have been raised about the drug having an effect on body weight. Your colleagues think either weight gain or weight loss might be a side effect, but they're not sure. To address these concerns, you conduct a laboratory experiment. You weigh 12 lab rats, expose them to the new drug, and weigh them again after a period of time. Let's say that at the end of your experiment, you're looking at a simple data set that looks like this. It's a record of the weight change for each of the 12 rats in your experiment. You would likely summarize the results by calculating the sample mean like this. And the sample variance like this. But what conclusions can one make based on these numbers alone? If you took these numbers back to your colleagues, in the absence of any additional information, I dare say you'd have done little to alleviate their concerns. While the sample mean suggests weight loss has occurred, the sample variance shows that there's some spread around the sample mean. Given this spread, a reasonable person may still wonder if the sample mean of negative 0.65 simply reflects natural variation, and maybe it was just negative by luck of the draw. Does negative 0.65 grams, in this case, represent a significant change in weight? How are we to decide? Well, here's one suggestion. We can use the data we've collected to drive the construction of a model. In this case, the model we build will be of the experimental process itself. We imagine a scenario in which our experimental results form a benchmark for a test aimed at deciding whether a drug, any drug, has an effect on weight. Our imaginary test would go like this. We would repeat the experiment exactly, but with a new drug. If the results from the repeated experiment are more extreme than the benchmark provided by the real numbers we recorded, then our test would be positive. A positive result here would mean that the new drug we tested did have an effect on weight. This is all hypothetical, of course. The point is that if the test we propose to conduct in this hypothetical scenario is a good one, then the benchmark established by the actual experiment we conducted would be a reasonable threshold to use in a universal test. That universal test would be aimed at detecting a drug's effect in replicated versions of the experiment. If we do indeed have a good test, then we would conclude that the original data we collected could be used to reject the claim that the original drug we studied has no significant effect on weight. I should add a few points here to nail down some of the important assumptions of the model we will construct. First, what do we mean when we say more extreme? More specifically, what's the basis for the comparison here? Following previous videos, what we'll do is imagine comparing ratios of sample means to sample standard deviations. If x bar over s generated in the repeated experiment is greater in absolute value than 0.65 over the square root of 1.5682, then we'll record a positive test result. Second, what do we mean by a good test? Here, our definition of a good test will be one for which the probability of a type 1 error is small. In other words, the probability of achieving a positive test result for a drug that actually has no effect will be small. Finally, given that we're focused on type 1 errors, our model will assume we've repeated the experiment using only drugs that have no effect on weight. In other words, placebos. So here's how we'll roll out the model itself. We'll create a benchmark using our data. Let's call that benchmark capital T for test value. Given the data we actually collected, the benchmark will be the absolute value of negative 0.65 over the square root of 1.5682, or about 0.519. Next, rather than going to the trouble of repeating the experiment in the lab, we'll simulate it on a computer. We'll generate 12 random numbers, where each random number represents the weight change experienced by each of the 12 rats in the new experiment. We have to be careful and remember that in our repeated experiments, we're assuming the drug has no effect on weight. So, the random numbers we generate should have an expectation equal to 0. We're also keeping everything else in the experiment the same, so the variation in the data from the repeated experiment should be comparable to that in our original experiment. We'll capture this feature by assuming the random numbers we generate come from a distribution with a variance equal to 1.5682. Once we generate our random numbers, we'll use them to calculate a sample mean x bar and a sample standard deviation s. Then, we'll compare the absolute value of the ratio of these two numbers to our test value of 0.519. As we've said, if the absolute value of the ratio of the mean to the standard deviation of the randomly generated numbers is greater than 0.519, we'll record a positive test result. Given that we've got a placebo, though, any positive test result we obtain will be a false positive, and so will represent a type 1 error. If we simulate over and over again, we can ultimately get a good estimate of the probability of committing a type 1 error, and so arrive at some conclusion about the drug we're actually interested in. Let's now see how we could do just that using a spreadsheet. Here's a spreadsheet that shows 8 simulated repeats of the experiment with a hypothetical drug that has no effect on weight. And here is one group of simulated changes in weight for each of 12 rats. For each cell in this block, I generated a pseudo-random number from the uniform 0-1 distribution. Then, I passed that number through the inverse of the cumulative distribution function for a normally distributed random variable. Incidentally, the probability density function of a normally distributed random variable has that classic bell shape. What's important to recognize here is that the random weight changes have come from a distribution with expectation 0 and variance 1.5682. Moving on, you can see I've calculated the sample mean x bar and the sample standard deviation s for the repeated experiment. When I divide the sample mean by the sample standard deviation, I get negative 0.168. Since the absolute value of this number is less than my benchmark of 0.519, my test is negative. As you can see, most of my simulated experiments have led me to correctly conclude that the drug has no effect on weight. However, one simulated repeat has resulted in a false positive. Based on these simulations, I might estimate the probability of committing a type 1 error to be 1 over 8, or 0.125. I can get a better estimate, though, if I simulate many more experiments on the computer. When I produce 10,000 repeated experiments, I find that about 1 in 10 produce a false positive. So, 0.1 would be a better estimate of the probability of committing a type 1 error. Like I said, based on 10,000 simulated repeats using a hypothetical drug with no effect on weight, I estimated the probability of committing a type 1 error in our hypothetical test to be 0.1 or 10%. Statistical convention says that a type 1 error rate above 5% means that the hypothetical test we've proposed is not a good one. It's just too prone to generating false positives. Ultimately, then, convention says that our data do not provide us with enough evidence to reject the possibility that the original drug we studied has no effect on weight. To put it slightly differently, the concerns your colleagues at the pharmaceutical company have about the drug's effect on weight are not reflected in the lab data you collected. This is a good place to stop, so let's recap. We began the video by asking, what do data collected in an experiment really tell us about drug-induced weight changes? To answer this, we used computer simulation to model the experimental process itself. Specifically, we estimated the probability of committing a type 1 error in a hypothetical test that used our lab results as a benchmark for making conclusions about other drugs. Ultimately, we saw that convention meant that the numbers we were working with were not enough to eliminate the possibility that the drug we studied had no effect on weight. Once you've wrapped your head around the ideas presented in this video, you'll be able to do one key thing. Given a dataset consisting of some number of observations, you'll be able to make an inference about the expectation of the underlying distribution by estimating the probability of a type 1 error. As you reflect on this outcome, keep in mind that in this video, we decided we could not reject the possibility that the distribution underlying the weight changes in the 12 rats we observed had an expectation of 0. I've said so many times that just watching videos isn't enough to come to terms with the material in this course. This is especially true for the material presented in this video. Read the notes, try the problems, and show up to our meetings prepared. That's a definite recipe for success.